third example for class class 16. It's class 16. And this is from Schaum's Outlines. Can I move my screen here? Yeah, I can move it. So Schaum's Outlines. If you're not familiar with Schaum's Outlines, I wish I had them. They're all in my office. I have a large collection of these books. They're fairly inexpensive, about $15 to $17 each. You can find them on Amazon. Do a search on Schaum's, Schaum, Schaum's Outlines. They're kind of old. They've been around for a long time, but they're like Spark Notes or Cliff Notes or whatever you're for courses, not just engineering courses. Actually, they have them for like economics and all kinds of chemistry and all kinds of math classes. Some of them are better than others. Some of them not all that great. The dynamics one, I've used some problems out of it, but I was never satisfied with those problems. In fact, that's one reason why I wrote my book. Hopefully I'll hear back from the publisher. I submitted it, but I don't know the first draft. I don't know if they're going to review it or not, or someone's going to look for all the mistakes that's all buried all over the place. But I wanted more examples. That's always wanted as a student. I always wanted the professor to give me more examples. I wish there were more examples in the book, and sometimes I wish there were harder examples. So that's one of the things that I've tried to put into the course and tried to also put into my my book, to make examples that were more difficult, because every student, I think everywhere, said, well, the homework problems were way harder than the examples, and the exams were way harder than the homeworks or the examples. And how was I supposed to know how to solve these problems? And I get it. I had the same arguments, had the same complaints. So I try to do my best to try to make difficult examples. But we need to have some simple examples so that you could kind of get the basic idea and try to have a mix. So that's my thought process. But just to mention this useful resource, Schaum's Outlines, it can really help in a lot of classes, especially if the book isn't all that great, the professor isn't all that great. You could have this extra resource for just a couple bucks. And you can also find them online, I think, in many places. And I know if you happen to have an Access Engineering account, or they give it to you free sometimes if you join like ASME, or that Access Engineering has a bunch of these Schaum's Outlines actually online for free. Anyway, back to the problem. We have this disc again with a rod that's attached here, and somehow it's this 8-foot bar that's huge. This 8-foot bar at AB is connected to a frictionless pin. That's nice of them. And to a 4-foot diameter cylinder. I don't know what this thing does and where you would see this in the real world, which is rolling with a constant velocity of 12 feet per second down the plane, right? So they're saying it's going this a ways. Right there, it's going at 12 feet per second, constant velocity. That's jump on that constant velocity, and the plane's incline at 30 degrees right there. Okay, the end at A slides on frictionless plane, which makes a 60-degree angle with the horizontal. For the phase shown, with the bar horizontal, determine the angular velocity and acceleration of the bar. Okay. So I already have the solution of this written out, so I'll again narrate through there. I made the thing smaller, and Schaum's gives us the answers. Sometimes Schaum's will work the problems all the way out, and sometimes they'll just provide the answers. And I think this one was the kind where they didn't actually work it all out. So here, and what I do caution you about is Schaum's does their own methods for things at times, which can deviate from what Beer-Johnston and our conventions. So the first thing I want to do is a velocity analysis. I said velocity and acceleration analysis of B, right? Because B in this case is really we could treat, because it is a rolling thing. It's got an instantaneous center of rotation right here at where it's in contact with the ground. So we do this little ICR thing, and by the way, it's saying that it's rotating at a constant velocity. Therefore, its angular acceleration is 0. Therefore, the tangential component of its acceleration is also 0. These are things that we could pick up. As soon as we draw this diagram, we could start thinking those things through and recognizing that it's true. So we could find the velocity at c. Well, no, we know the velocity at c, right? It's 12 feet per second. But now we can find the angular velocity because it's going to be that velocity at c divided by this distance between the center and point D, which is also the ICR. So we take that 12, and that's divided by 2 because it's a 4-foot diameter disk. So that ends up at 6 radians per second, and we see that it's counterclockwise. We can also find the velocity of B now. We know that because we have the angular velocity, we just multiply it now by 4 right here, because now it's the distance between B and D is 4 feet, and we have that angular velocity of 6 radians per second. We get 24 feet per second. As I mentioned, the tangential acceleration at that point is going to be 0 because the angular velocity is 0, and that's because the translational acceleration is 0 here at c. But we do have an acceleration at B because of the normal component, right? So we want to make sure we don't forget about that normal acceleration. It's the thing that comes and bites us, right? So that's going to be omega squared times r, or that's 6 radians per second squared times 4. So we get 144 feet per second squared, and it's pointed downwards from B towards D. So we do the rod velocity analysis right here, and I want to use ICR. That's the easiest way. We already have the direction of VB right here and the value. So drawing a line through it that's perpendicular, and we also know that A is traveling either up or down. We don't know actually initially whether this is up or down. We could kind of guess, but we might not know. We do know that we could draw the line that's perpendicular through it, and we can see where it connects. Now, as soon as we know this line right here, and we see, well, as soon as we know the ICR, we're able to find what the angular velocity of that rod is going to be, because we just divide this velocity by this distance right here. But also from this diagram, we could now come to the conclusion of what direction the velocity at A has to be. And that's because it's rotating about that ICR. We can see that it has to be going up the plane. And we might have been able to use our intuition to find that. But it's often important to confirm our intuition or to reform our intuition if we are come to something that goes counter to what we guessed initially. So we have to use a little geometry here, and we're able to find the distance right here of B with respect to the ICR time. That's going to be the length of this thing times the sine of 30 degrees. And from that, we're able to find what the angular velocity of this is, also 6 radians per second. It's a coincidence because of geometry and the location the thing happens to be. But also note that it's going to be a clockwise 6 radians per second, as opposed to where this disk was actually a counterclockwise 6 radians per second. But it's just a coincidence that they're both 6 radians per second. And now we do an acceleration analysis of the rod. And I think I went back after I was done and discovered which direction this acceleration A was going to be. Or maybe I just guessed that it was going to be down there. We note that we know the acceleration of B is at that 30 degrees, and because of this orientation right here, we also see that the A has to be accelerating along that line. It can't accelerate into or out of a surface. Acceleration is tricky because a lot of times we could be fooled by thinking that there's a constraint on the acceleration that isn't necessarily true. But one thing we can always do is think about, what is the position in the next instant going to be? That's one of the things that can help us in acceleration to try to work our way through, what direction something is going to be, or what direction is constrained to not move. You have to ask yourself, what's the position the next instant or a second later? And is it possible for this thing to accelerate in any other direction than up or down this wall? And the answer is no, because otherwise it'd have to be leaving contact with the wall, or it had to be passing through the wall. So it has to accelerate, because that's what the next instant. I think I beat that into the ground. Anyway. So we do this diagram for the thing, and we write out, we're trying to find A, and we know B, so we write the thing out for this end of the rod. So the acceleration of A is equal to the acceleration of B, right, that we've placed B at both spots, plus the tangential and normal components of acceleration right here. And so in the x direction, writing that out right here, we have A, right? So, and once again, I chose, did I say this right? Yes. Okay. So what I went ahead and did is I took the component of the component, and I chose it to be a positive, I guess, in the x direction was my initial thought. And I put them together with the, let's see, why does it have a, okay, because I have these over here. Okay, so I drew out what my normal had to be and my tangential acceleration components, and I saw in the x direction that there was no tangential portion of the tangential component was not, the component of the component in the tangential direction was 0 right here, right? And then also the normal acceleration was completely in the horizontal direction, and we knew that it had to be to the right here. So we're able to find what this value is. And we get a positive answer, so we guessed correctly that it was actually accelerating downwards, which doesn't mean that it's going to be moving downwards. It means that its velocity is going to be less, right? So it's decelerating because it has so much of velocity. It has a velocity at this moment right here. See, that velocity is actually going up the slope, but it's going at a slower and slower velocity because we had this positive acceleration. So that's what that means, right? We've got to interpret what these things are. And then in the y direction, now that we know what this acceleration is at A, we're able to put it in here and break it down. And when it's negative here, because it's you notice looking at the diagram, it's negative. And then there's also have a negative component right here, a negative part of B right there. So it's and then we have the tangential though is going, we drew it as positive. I drew it like here. So my guess right up here was going to be positive. So I think I forgot to, I wrote it out here, but I didn't read it. Yeah, we guessed the angular acceleration was clockwise. Just why? Well, it just seemed like, hey, I think it's going to be, and then we found out it was the other direction because we find that it's a negative answer. Therefore, we had guessed it wrong. And so then we answer the problem because they were looking for the angular velocity and acceleration of the bar. But by the way, that wording is a little, Is the angular velocity and the acceleration, or is it the angular velocity and angular acceleration? Well, it turns out from the answer that they gave you, they meant the latter of the thing. But if we did need to know the acceleration of the bar, well, we found the acceleration at both points. Sometimes you can make the case you actually want the acceleration at the center of gravity would probably be the most reasonable thing to try to identify. Or to be asked, if you were going to ask for it, what's the acceleration of this bar? Well, they didn't say a particular point. Probably do it at the center of it, and then also report what the angular acceleration was going to be. But this is what they asked, and look, we got the right answer. So that's another problem. We're going to do class 17 is going to be mostly examples, continuation, and a little bit harder examples, right? So these were like a single bar, or I guess in this case we had two pieces. I guess in the other one we had two pieces, but I'll do some more complicated problems. Now, so we're mixing up which guitars that we're taking a look at, the tour of guitars. Now, this is one that I built out of parts and purposely made backwards, right? Jimi Hendrix was a left-handed guitarist, and although there were left-handed guitars in existence in the years that he was active, which is really probably 1967 through 1970 when he passed away, but he played a right-handed guitar, but he had to restrung so he could play it left-handed. And so this is sort of a Jimi Hendrix tribute. And he set a couple guitars on fire, notably at Monterey. You might see an iconic picture of him kneeling before a guitar that he's set on fire on the stage. So I've actually made this purposely look like it was charred up. And I think what the interesting part to me is that I found a decal for Fender. So I made this out of parts from a company named Warmoth, but I found a decal that was reversed. And one of my very favorite parts of Hendrix was the delicate stuff he did. He did a lot of psychedelic things. I think I turned the tone knob down instead of the velocity. There you go. And so this is a little bit of a tune from Pearl Jam, which is, of course, not Hendrix, but they were heavily influenced, at least I think Stone Gossard, that guitarist was. But this is from Yellow Ledbetter, so I've always liked he purposely tried to sound like Hendrix here, so this is why. So see, I'm not playing that well. Okay, let me put it in between pickup, so it's like a delicate, pretty sound, so a little different from Van Halen. So anyway, I really like that song, Yellow Ledbetter. Look it up, Yellow Ledbetter by Pearl Jam. It's kind of funny that the lyrics of it, they've never printed out what they are, and he mushmouths most of them through there. So there's a lot of really good funny videos on YouTube where people have tried to interpret what he said when they put little different images in there in the misunderstanding of the Pearl Jam lyrics. But it is a really cool song. And for Pearl Jam fans, I think it's a really popular song. Sort of an obscure one. It didn't actually appear on an album. But anyway, so that was your little guitar educational moment there. A little unnecessary additional piece of information. How long did that video take? Oh, that was an 18-minute video. Of course, it had a lot of unnecessary guitar stuff in there. But then there's a lot of stuff in class where I use your time in a non-dynamics way. So why stop now? Anyway, I hope everybody's doing well. And thanks for your patience. And work on the problems that are assigned, and come back and look at the videos. I don't expect you to be watching these all the way through. In fact, I kind of putting these little Easter eggs in there just to see who actually watches them. But take care, guys.